Video, I'm going to continue to talk about solution stoichiometry. This is part 2 to a video, so if you did not watch part 1, you probably want to go watch that because we started this question already. So in this part, we're going to find the concentration of each ion left in solution. To review, our problem started with you had 100 milliliters of each solution, and we found that we were going to make 0.9 grams of calcium hydroxide. And we found that KOH was our limiting reactant and CaNO3, calcium nitrate, was our excess reactant. And knowing this is really important, as well as knowing how much of each ion you started with, or what was the initial values. Those are really important. And so I'm going to come back to this, and let's label a few things. The first thing I want to label is that KOH we found was the limiting reactant. And so what does a limiting reactant mean? That's the reactant that runs out. That controls how much product you can make. And calcium nitrate was our excess reactant. I also am going to label how much calcium hydroxide we could make. That was 0.926 grams. And then I'm going to write the initial amounts of each reactant underneath here. And how I got the initial amounts, again, was just molarity times the volume of that substance. So we started off initially with 0.025 moles of KOH. And then initially 0.055 moles of When it comes to solution stoichiometry, sometimes it might be helpful to write a net ionic equation. Or let's look at what happens to the ions in solution. So these substances are both aqueous. What does that mean? That means that when you put them in water, they dissociate. So the K actually separates from the OH. And so let's write the ionic equation. That gives us, we have 2 potassium ions and 2 hydroxide ions. They are separate, they're not together. The calcium nitrates dissociate in solution. So we've got a calcium ion, and then we have 2 nitrate ions because that's subscript. They're not together. And that will make, those are dissociated, so 2 potassium ions plus 2 nitrate ions and our calcium hydroxide, which stays together because it's a solid. That has a 2 out there. And so why did I do this? Because we want to find the concentration or the molarity of each ion left in solution. It's important to look at our ionic equation because when you look at it, you can see the spectator ions or the ions that are not involved in the reaction, and they are potassium starts aqueous and ends aqueous, and nitrate starts aqueous and ends aqueous. And I want to talk about each ion separately. So let's start with the potassium. The potassium started aqueous and it ended aqueous. It did not have any part of making this solid. K is not in that formula. And so even though we called KOH the limiting reactant, potassium is not limiting because potassium doesn't do anything. It was aqueous before, it stays aqueous. And we know law of conservation of mass, matter cannot disappear, it can't be created or destroyed, and so the amount of potassium that we start with equals the amount that we end with. Okay, well, how much did we start with? Well, let's go back to our initial amount. We initially had 0.025 moles of KOH. Well, let's look at that formula. Every 1 mole of KOH has how many moles of potassium? Just 1, because potassium does not have a subscript. So I actually started with 0.025 moles of potassium ions. And if I started with that many, that means I ended with that many. The coefficients in front don't matter. Now the question asked for the molarity of each ion. Molarity is moles per liter. And so what happened with this problem? We had 100 milliliters of this, and we had 100 milliliters of that, and we mixed them. And when we mix them, you get a final volume of 200 milliliters. Volume can't disappear. And so you have to make sure to get the molarity that I don't divide it by 100 milliliters. I'm going to divide it by 0.2 liters or 200 milliliters because that's how much I finished with. And so when I do that, that will give me 0.125 molar potassium concentration. Let's look at that again. Because it's a spectator ion, the amount you start with equals the amount that you end with. So I went back and I looked at how much potassium hydroxide did I start with. Okay, that means I had that many moles of potassium ions. Divide by total or final volume. Let's repeat that with the nitrate, because nitrate was also aqueous before and aqueous after, so it was not used at all. The amount we started with equals the amount that we ended with, because it didn't make any part of that solid. I did not start, I started with 0.055 moles of calcium nitrate. Now, we do need to pay really close attention because it has a subscript that tells me that every 1 mole of calcium nitrate has 2 moles of nitrate ions. Because that subscript means that there are 2 of those in every one of the whole thing. So that ends up being at 0.11 moles of nitrate initially. Because it's a spectator ion, the amount of moles that we start with equals the amount of moles that we end with. And to get the molarity, we just need to divide that by the final or the total volume, which was, again, 0.2 liters, which is, you ended up with 0.55 molar for your nitrate ion concentration at the end. So those were our spectator ions. Let's go back and look at the other ions. So we called KOH the limiting reactant, but as we discussed earlier, K wasn't actually limiting, it didn't do anything, it was aqueous before, it stayed after. So really the true limiting reactant is the OH. And your limiting reactant again is the amount, the ion that controls how much product you get made because it gets used up first. So whatever ion is your actual limiting, that one ran out. There is no hydroxide left. All of this was used to make that because that's the real limiting ion. So the concentration of hydroxide left in solution should be 0. There's none of this left. There's my limiting reactant, so all of this became that. But this was my excess reactant. And as we said earlier, none of the nitrate was used, but some of the calcium was used to make that solid. Not all, but some of it was used. That's what an excess reactant is. Some gets used. And so we need to figure out how much is left over, because some of this became that. But there are still some calcium ions in this solution because it was the excess reactant. And so how we solve for this is we need to figure out how many calcium ions that we started with. And then we're going to subtract the amount of calcium ions used to make the solid, or to make the calcium hydroxide. And whatever the difference is between those is the amount of calcium that's left over, or that's still in solution. Okay, so let's go look back at the initial problem. How much did we start with? Initially, we had 0.055 moles of calcium nitrate. 1 mole of calcium nitrate has 1 mole of calcium. calcium does not have a subscript, so we don't double it or anything. That leaves with, we initially had 0.055 moles of calcium ions. I'm going to go put that number right up here. We started with 0.055 moles of calcium. I need to figure out how much calcium I used to make my calcium hydroxide. Well, if I look back and I labeled everything nice and neat, I know that I made 0.926 grams of calcium hydroxide. And change that to moles. By looking back at my past problem, the molar mass of calcium hydroxide was 74.096 grams. And this is where, if your work is nice and neat, it makes things easier because you can go back and find the numbers easily. If it's really messy and you don't have things labeled, it can be difficult to figure out which number was which. So I really suggest you stay organized. Now, I don't want moles of calcium hydroxide used to make this. I want moles of calcium. And so 1 mole of calcium hydroxide. Calcium does not have a subscript, so has 1 mole of calcium ion in it. What does that tell me? That told me that we had used 1.25 moles of calcium to make that. That's my used value. Let's go back here. Now, to get how much calcium is left over, I just subtract the amount I started with minus how much I used. Leaves us with 0.0425 moles of calcium are left over. Now, the question did not ask for moles, it asked for molarity. And again, we divide by the total volume. You should get the leftover molarity is 0.213 m. So I hope this video was helpful. This is really tricky because you need to be able to identify which reactants are spectators and not used at all. So the amount you start with of them is the amount that you finish with. You have to pay close attention to subscripts, and then you need to be able to identify which ion was actually limiting, like my hydroxide, and which ion we have some left over of. Keys with this are really to make sure your work is neat, so that way you know what all of your numbers are, because there's a lot of numbers, there's a lot of ions. Pay close attention, label everything, and you'll be less likely to make mistakes. I hope this video helped.